Okay. So in 2D flows, 2D flows, okay, potential flow. So potential means incompressible, rotational, rotation. So this is velocity is like this. This is del cross U equal to 0. So such a flow is potential flow, and in 2D flows, we know that there are two scalar functions. You can represent the flow, represent this flow by two types of scalar functions. What are those? There is a phi of xy and psi of xy. So as far as phi of xy is concerned, you have u equal to dou phi by dou x, v is equal to dou phi by dou y. Okay, these are Cartesian. Maybe if you want a radial component, dou phi by dou r, u theta is equal to dou phi by r dou theta. So the velocity components are defined using phi like this. Similarly, for psi, also we have u is equal to dou psi by dou y. And v is equal to minus dou psi by dou x. And if you want to write ur is equal to dou psi by r dou theta, u theta is equal to minus dou psi by dou r. So this also for stream function, right? And with respect to phi of xy, with respect to phi of xy, you know, dou squared phi by dou x squared is equal to dou u by dou x. And this one, dou squared phi by dou y squared is equal to dou v by dou y. Differentiating this one with respect to x and this one with respect to y. And dou squared phi by dou x squared plus dou squared phi by dou y squared is equal to dou u by dou x plus dou v by dou y. Dou v by dou y. And this is the continuity equation and equal to 0. So because of the del dot u equal to 0, del squared phi is equal to 0. That is incompressible continuity. Because of incompressible continuity, del squared phi is equal to 0. Now come to the stream function. So here that means phi is a function that satisfies. Phi is a function that satisfies. So phi satisfies Laplace equation. So such functions are called harmonic functions. Similarly, come to here, differentiate the first the u with respect to y. So dou u by dou y is equal to dou squared psi by dou y squared. Differentiate this with respect to x. Dou v by dou x minus dou squared psi by dou x squared. So what is dou u by dou y? Dou u by dou u by dou y minus dou v by dou x. What will be? Dou squared psi by dou y squared minus minus is plus dou squared psi by dou x squared. So what is this? This is the component of vorticity along the z direction. Irrotational flow, omega z is equal to 0. So this is equal to 0. So irrotationality gives del squared psi is equal to 0. Incompressibility and continuity equation gives del squared phi is equal to 0. So psi is also harmonic, satisfying Laplace equation. So altogether we can say that in 2D potential flows, the functions phi of xy and psi of xy are harmonic Laplace equation. And now we bring into the theory of complex variables. So in theory of complex variables, suppose you are having two functions which satisfies the Laplace equation or they are harmonic, then if we join them by phi of xy plus I into psi of xy, I into psi of xy, then this combination of two functions with an I in between, I is equal to square root of minus 1, that gives you a function of z, f of z, which is analytic. So this is a function of a complex variable. Fz is function of a complex variable. So we are having function of a complex variable where z is equal to x plus I. So when you are having two functions which satisfies the Laplace equation, we can combine them. The two functions of two variables each can be combined to write it as a function of a single variable z, where z is a complex variable. The z is called a function of a complex variable. So this is a kind of simplicity we are going to get in the analysis of problems by using complex variables. So we'll see a simple example. Fz is equal to log z. So this is the function. And z is equal to x plus iy. You can also have r cos theta plus I r sin theta in polar coordinates. So r into cos theta plus I sin theta. This is equal to r e raised to I theta. And we can write as logarithm of r e raised to I theta, which is equal to log r plus I theta. And r is equal to a squared plus y squared the whole raised to 1 by 2. And theta is equal to tan inverse y by x. So like with that it becomes logarithm of x squared plus y squared plus I into tan inverse y by x. So as per our definition, this is phi of xy. This is psi of xy. So let us see what kind of a flow is described using phi of xy is equal to half of logarithm of x squared plus y squared, and psi of xy is equal to tan inverse y by x. Right. So you can identify the flow by using these functions if you plot by plotting the iso contours. Iso potential. That is phi is scalar potential, iso potential lines. So iso streamline, iso stream function line, iso stream function. Iso stream function is also called streamlines. So if you plot the streamlines, you can identify the flow as the fluid will be flowing along streamlines. No fluid particle will be across the streamlines. So the velocity across a streamline is equal to 0. So with respect to isopotential line, fluid will be flowing across potential lines. That is normal to the potential line. Suppose you are having an isopotential line, the fluid flow will be at that point, the fluid flow will be normal to the isopotential current. So it's like that. So like that we can identify. So what is this? Now you try to draw an isopotential line. How to draw an isopotential line? You give a constant value for phi. So half into logarithm of x squared plus y squared is equal to, you take it as a constant c1. Then what is log x squared plus y squared? Log x squared plus y squared is equal to 2c1. What is x squared plus y squared? Equal to e raised to 2c1. Where c1 is a constant, 2 is a constant, e raised to that is again a constant, take r1. Oh, this is a constant. What is this? What is this curve? S squared plus y squared is equal to some r1.
Circle.
It's circle. So it's a circle, right? So it's a circle. So okay, this is an isopotential line. This is an isopotential line. X squared plus y squared is equal to r1 squared. Is an isopotential line with radius r1. Okay, with radius r1. So like that. If you draw another one at some r2, so it will be another circle. Like that. So this is s squared plus y squared is equal to r2 squared. So like that. So how the flow will be? At any point, it is normal to the isopotential line. So what is the kind of flow you are having now? So it will be, flow will be like this. So it's a radial flow emanating from the origin, center. So emanating from the center. This is a source flow. This is called a source flow. So then what is the complex flow potential for a source flow? It is log Z. So log Z is the mathematical representation of a source flow. So W is equal to log Z. The function Z is a complex variable. Function of the complex variable gives this represents source flow. Now, if you look at the streamlines also, by seeing the streamline also, we can establish the same fact. So what is when psi of xy is equal to constant, psi of xy is equal to some constant, say a1. So tan inverse of y by x is equal to a1. What is y by x? Y by x is tan of a1. So this a1, I will change the a1 to some theta 1. A1 to some theta 1. So tan theta 1. So y is equal to x into tan theta 1. What is this one? What is this one?
Straight line.
This is a line passing through the origin, right? Having a slope tan theta 1 or making an angle theta 1. So this is theta 1. So this is a streamline. This is a streamline. What is the meaning of streamline? Fluid will be flowing along the streamline, not across. So the same fact is again recovered. So the phi as well as psi, right? Both is embedded in the same complex flow potential, and it represents the same flow. So like that, you just see what is this. I will write f is z. F is z is equal to some gamma by 2 by logarithm of z. What I into gamma. There's an I is also there. So what this represents? What this complex flow potential? what flow this complex flow potential represents. So you can again find this is multiplication of I. So the multiplication of I will make the streamline. This multiplication of I will make the stream function same as or similar to what is the isopotential of this. And the I multiplication is there where I is earlier multiplied by psi, that becomes okay -1, so that becomes the phi, and this phi becomes psi. So that is the interchanging. So interchanging, what is the meaning of interchanging? The streamline becomes the isopotential line, and isopotential line becomes streamline. So what is in that case? This becomes a streamline. So it's a circular motion. So this is a this is a complex flow potential of free vortex. And if you write in this form, this gamma represents the strength, the circulation. So this also, this source flow also we can write with the strength Fz is equal to m by 2 pi log Z. If you write the m represents the strength, which is the volume flow rate. Volume flow rate. Volume flow rate. So now you can remember what is the complex flow potential for a source of strength m by 2 pi log Z. What is the complex flow potential for a vortex flow of strength or circulation gamma, right? I gamma by 2 pi log Z. So these some of the flows you can just remember what is the kind of flow complex flow potential. Fz is called complex flow potential. Fz is called complex flow potential. So what is Fz is? Fz is basically phi plus I psi. Phi plus I psi. So Fz is phi plus I psi. So my pen is charge is not there. Let me wait for 1 minute so that it gets charged. So this is what is the introduction about complex flow potential, and the application of complex flow potential makes the analysis of potential flow problems very easy. So compared to any conventional any other method. So these topics you have studied in complex variables, where you studied this separating a complex function of a complex variable into real and imaginary part. So now that in fluid mechanics, the real part can represent the scalar flow potential, and imaginary part can represent the stream function, right? So phi plus I psi. Now you also see how. Oh, okay. Now that you have studied, now that Fz is there. So Fz is Z composed of x and y, right? X plus I. So some Fz is there. Z is equal to x plus I. So what is the what is the equation for f dash Z? Do you know what is f dash Z? So if Fz is analytic, we can find it f dash Z. So this Fz is phi plus I psi. What is f dash Z? So it is dou phi by dou x plus I dou phi by dou. Sorry, not phi. I dou psi by dou x. This is the equation for f dash x. Now differential f dash. So this equation we must remember. So this is how the differential of an analytic complex function f dash is equal to dou phi by dou x plus I into dou psi by dou x. So what is dou phi by dou x? Is u, horizontal component velocity. What is dou psi by dou y? minus v. So what is that f dash z represents the real part of f dash z represents the horizontal component of velocity. The negative of the imaginary part gives the vertical component of velocity. So f dash z is that f dash z is called a complex velocity. Complex velocity. Okay. So it's called a complex velocity. Okay. So this is very much useful. So you don't have to find out f z. If you can find out f dash z, then directly it will give you the components of velocity. Now, how do you write this in polar coordinate system? Polar coordinate system. U is equal to, what is u in the polar coordinate system? U and v in polar coordinate system. So you have this is ur. So this is some theta. So and there is a u theta also there. There's a u theta. So this is 90 degree and this is parallel. This is 90 degree and this is 90 degree. So this will be, this is again theta. So what is u? U is equal to, this is u theta. U is equal to ur cos theta minus u theta sin theta. And v is equal to, v is equal to ur, this is 90 minus theta, ur sin theta plus u theta cos theta. Now we substitute f dash z. F dash z is equal to u is ur cos theta minus u theta sin theta minus I into ur sin theta minus u theta cos theta. Okay, so I into, here also I is there. So you write ur, what is ur into cos theta minus I sin theta minus u theta this is minus u theta into I cos theta plus sin theta. So have an I here and divided by I. So that is ur e raised to minus I theta minus I u theta cos theta. 1 by I is minus I sin theta. So that is equal to ur e raised to minus I theta minus I u theta e raised to minus I theta. So ur minus I u theta into e raised to minus I theta. So in polar coordinate system, f dash z gives so what you do, you take f dash z, you multiply it by e raised to I theta. That gives you ur minus I u theta. So this is that's a difference in polar coordinate system. The f dash z you take, then multiply with e raised to I theta, that gives the ur minus I u theta. Whereas in Cartesian coordinate, f dash z directly gives u minus I. So this is a conversion. So this also you remember. So we'll continue in the next class. In that next class, we will study what is a doublet. So we will close the class for today. I think so. There are only 6 students in the class till the end, right? So someone only Biswas was trying to join in between. I did not permit.